Thank you. So yeah, I'm Luis, and normally I'm talking about MEV kind of exclusively, or Shutter as an MEV protection mechanism. But today here I'll keep it a little more broad on basically this commit and reveal problem. Yeah. And yeah, I'm the product manager at Shutter. I work at Brainbot, but Shutter is a project at Brainbot. I'm the product manager. So anything more deeply technical, maybe you should, maybe we can defer the question to Yannick, who's also in the audience. Yeah. So does that work? Oh, yes. So more broadly speaking than MEV or is Shutter, this mechanism enables users to safely reveal private information to the chain. And this is something Yannick came up with, so credit to him for this, basically. So the issue is right now, basically, if you were to try to safely reveal something to the chain that was previously private, it's not possible, right? So you're trying to do this, and then someone else basically steals your information away. So I'm trying a little bit here with stable diffusion. So basically, without Shutter, you have everyone looking at your information that you're trying to reveal to the chain, and they can take it away from you before you've even revealed it to the chain, essentially. With Shutter, you can safely reveal it to the chain. So I think it's cool that Stable Diffusion came up with a female god. So yeah, and then the solution, very broadly speaking, is threshold encryption to prevent front running, but also a bigger sort of set of malicious behavior on chain. For MEV, and I basically have three different exhibits, and the first one will be MEV. So for MEV, we want to go from some sort of a chaos situation on MEV. Here I'm saying like bots are fighting other bots, and Flashbots is fixing that to a great extent, but we still have a suboptimal sort of situation. To here, where we want to have transactions be shielded. We want to encrypt transactions, and they can be batched and signed by the block producer while they're still encrypted, such that the block producer, whoever they be, validator or sequencer, can't even see what's in the transaction, so they can't censor or front run. And then, broadly speaking, we're using threshold encryption to ensure the actual decryption step. So we need to enforce the decryption, and we don't want to have a centralized entity doing this. So threshold encryption essentially makes sure that is happening. There's enforced sort of committee-based decryption, and that also we don't have to trust a centralized encryptor or decryptor. And that's sort of how that works. So think of Shutter in the lower left corner as this sort of keeper system plus a DAO that creates keys. First, they create the encryption key, which is used to client side by the user to encrypt transactions. Then that can pass through the metaphorical dark forest. And then the keepers collaborate again. Basically, it's not really how that works in the depth in the protocol itself, but essentially think of they collaborate again, create the decryption key, which is then used to decrypt. So the keepers keep the transaction safe, basically. It's also a stable diffusion thing. And then for MEV, I think quoting Stefan, who we just heard, which is great. It's big. It's a big. There's a lot of MEV already. I don't think I have to define it because he talked about it. We are looking at this. We're looking at MEV. Basically, we're focusing on a subset of MEV. Specifically, we're trying to say there is a certain level of, there's a certain amount of malicious MEV, and we're trying to mitigate this malicious part of it, especially front running, sandwich attacks, censorship, and and we think that for the end user results in worse prices, failed transactions. And these are examples, and I'm sure you know these. And how we are working on this, or worked on this so far, is we implemented this aforementioned sort of encryption mechanism. First, we implemented it as an on-chain smart contract system that you can deploy in addition to to another smart contract that you want to protect. So this may be especially relevant here for a DApp focused conference. So that's ready and to implement. And it can have some use cases. The issue with this is that it's expensive on chain, and also it breaks composability for the transaction path essentially. So we're no longer focusing on that. We're focusing mainly on rolling shutter, which is this mechanism but implemented into the rollup sequencer transaction flow essentially. And we hope it makes the entire rollup be front-running or malicious MEV protected, and also adds this level of censorship resistant. For a centralized sequencer, we also add this censorship resistance level. So for the rollups, the rollups have this dilemma right now. They would say, oh, should we try to optimize for the MEV searchers, or should we optimize for the end user? And we're saying that's not an actual dilemma. We think there is a way to prevent the malicious MEV and allow through basically, or plug in with whatever the rollups chosen mechanism is to deal with MEV. So an example would be Optimism, who are using these MIVA MEV auctions. So something like Optimism could use something like Shutter to prevent the malicious part of MEV, and then use MIVAs or something like the flashbots for L2 basically to distribute the remainder of the benign MEV. So yeah, and that's the MEV topic. And I said it's going to be also different sort of aspects or use cases. So the other exhibit is shielded voting. So we're with Snapshot together. We've implemented again the same threshold encryption DKG mechanism, but this time not to prevent front running, but rather to ensure information symmetry basically in DAO voting. So essentially, right now the DAO voting is public and kind of that's okay to a certain degree, but also not okay to a certain degree because anyone can see what's happening, and it influences the voters' decision making if they see what's already happening, and someone who's voting later has more information available than someone who's voting earlier. So that's just the mechanism of encrypting transactions and then revealing them afterwards. And it's for the dApps, if we consider Snapshot not a dApp, but basically for them, it's a better commit and reveal scheme. So they could use a trivial commit reveal scheme, but Shutter in this case is better because there's only one transaction needed from the user. They only have to do one transaction in the beginning, and then it's automatically decrypted. And also there will definitely be the reveal. So there's no the user can't choose not to reveal, right? So that's how that will look like in Snapshot in the backend, in the admin backend, choose Shutter, and then the transactions will be encrypted. Yeah, and then the third example or topic, we just briefly touch on because only briefly touch on because it's complicated. Yeah, but essentially, via this mechanism, we also think that we can add this level of censorship resistance. Here is Martin saying that if you were to implement this threshold encryption mechanism basically at the L1 layer, you can, because the transaction will be encrypted, the validator in this case has a certain argument of plausible deniability, because you can say, well, I don't know what was in the transaction that I signed, so I can't be held liable for what's So we think it can benefit sort of censorship resistance at the L1 or also L2 level. That's yes. Talked about this, and basically, what we're doing there is it's a research sort of exercise for us, especially. And our next step is there. How can we? Because this proposal that Martin is talking about, that he also was really gave a lot of input on. That's for Ethereum sort of post-merge without PBS. So we're looking now how to combine it with PBS, and also there might even be benefits using Shutter and MEV Boost to reduce the trust assumption in MEV Boost. And I gave a talk about this at Stanford 2 weeks ago, I think. So if you're interested in that, then watch that talk. Yeah. So in summary, even broader than MEV, Shutter is this flexible kind of commit and reveal scheme, which can help mitigate all kinds of issues relating to front-running censorship and other sort of misbehavior on chain. And it's already, it's nearly live in production. Is a little bold here, but essentially should go live like this week, hopefully, for shielded voting. And then, for DappCon or for the dApps that maybe are listening, or dApp developers, they can implement Shutter directly as this on-chain smart contract version, or ideally kind of deploy at some point when we have that ready on a shutterized front-running protected rollup, or in the future maybe also on a shutterized L1 at some point. Yeah. So that's it.
So we've got about 12 minutes for questions.
Thank you for the talk. I have a question. Are you guys planning to implement a builder that is using Shutter as like their build strategy?
Yes, I think we discussed this as one of 3 different options on how to combine Shutter and PBS/MEV Boost. So maybe Yannick can say something specifically about that, but more broadly speaking, and which layer you implement it changes which problem you're solving. So basically, if we implement it deeply into the protocol, we would actually try to solve the actual front-running issues. If we implement it at the, I think if we implement it into MEV Boost at the builder level, essentially, I think we'd rather reduce the trust assumptions for in that context, not necessarily to actually prevent front running. But maybe is that correct, basically? Yeah. So that's not a super high priority for us, but could definitely something that we would also be interested in doing, yeah.
Besides running a builder, what other trust assumptions will Shutter solve between serger and builders, or between builders and relays?
So to answer this for MEV Boost, yeah. The hope would be that, because right now you have to trust this relay to a certain degree. So what we can do with Shutter, basically, we can improve the trust assumption of the relay. We can basically make the relay trustless. Yeah.
May I ask how?
Because the same mechanism as I described for basically making the rollup sequencer, or reducing the trust assumption of the rollup sequencer, making that kind of front-running and censorship resistant. Basically, because if the relay can't see the transactions while it's passing through, then you have to trust it less, essentially.
So the relay will not be able to steal MEV, to steal the block content, but there are more trust assumptions that are related to how the relay is taking decisions on the block builder that's been actually chosen. Is it related to that, or is it strictly to make sure that relays are not basically using the block content in order to run maybe a local builder their own?
I think the latter. Yeah? I think in that case we were trying to make the relayer be less trusted, or needing less trust.
Cool. Thank you.
So I feel like distributed key generation as like a thing on Ethereum has been pretty well understood and researched now for several years. It sounds a lot like most of this stuff is really just going live now and more recently. Is this really like the first time we're actually seeing DKG being used in Ethereum?
No. I think Parity developed a DKG, as you say, way back in 2017 or something. Yeah. So I think special about our implementation is about the cryptography protocol itself is the efficiency of it. So because we need to run it basically within a matter of seconds, so like 5 seconds to 10 seconds, I think is our target. So that's sort of the achievement there that we worked on with these cryptography professors, Sebastian Faust and Stefan Litzembowski, to make it very efficient essentially. But other than that, you're right. The threshold encryption and DKGs aren't something super exotic. It's basically well understood cryptography, and the novelty here is more to implement it into, well, for example, into the L2 layer or the voting, kind of the off-chain voting layer there. Yeah. And it's maybe also to mention it's not as, I think it's not as exotic as like, zero knowledge technology yeah. So we hope that it would be more, better understood, less complicated, more battle hardened than something like a really complicated zero knowledge proof. So.
Okay, that about wraps it up for questions. Still a little bit of time if anybody'd like to know, but otherwise, let's thank the speaker.
Thank you.